Greetings, Mr. Sutton here with the AB Calculus 2-6 Extra Practice Number 5 solutions on continuity. To find the interval of continuity on this function, we're going to first identify the discontinuities and then write our intervals around them. So we have a removable discontinuity right here, a hole at x equals -5. We also have an infinite discontinuity, an asymptote at x equals 0 right here. So then our intervals of continuity, we're going from -infinity to -5, union -5 to 0, union 0 all the way to infinity. Trying to find intervals of continuity on this function, we notice that there actually are no discontinuities. This is continuous everywhere. So that means our interval is just going to be negative to positive infinity. To find intervals of continuity for this function, we first note that there's a jump discontinuity at x equals -5. So therefore, our continuity interval, we're going to have one from -infinity to that discontinuity at -5, union -5 to infinity. On this one, we're trying to find all points of discontinuity and what type they are. Since this is a rational function, we know to look for holes and asymptotes, or removable and infinite discontinuities. But in order to figure out what they are and which is which, we need to factor this thing. So let's start with the numerator. Two things that multiply to -3 and add up to -2. That's x plus 1 and x minus 3. Downstairs, things that multiply to -15 and add up to +2. That would be x minus 3 and x plus 5. So now taking a look at what kind of discontinuities we've got, we see here that we have this x minus 3 factor repeated. Since I would get 0 over 0 by plugging in 3, since I can cancel these out, that means I have a removable discontinuity at x equals 3. Now the other problem is this x plus 5. Since I can't remove that factor, and -5 makes the denominator only undefined, that means I have an infinite discontinuity at x equals -5. For this problem, trying to find points of discontinuity, we have a rational function, so we're always on the lookout with these for infinite discontinuities and removables or holes. But in order to get either of those, we need to zero out the denominator. And x squared plus 1, well, x squared is always going to be either 0 or positive, and you're adding something to it. So there's no way this is ever going to come out as 0, which means that since we can't zero out the denominator, there are no discontinuities on this one. For finding discontinuities on this problem, we know with radical functions, or at least even radicals, square root in this case, we have an undefined area wherever the radicand, the stuff inside the square root, is negative. So if we set 3x minus 2 less than 0, that's going to help us figure out where that undefined area is. Well, solving for x, we just add 2, divide by 3. So we have an undefined area then for x less than 2/3. To figure out discontinuities for this rational function, we have to take note of places where the denominator is 0. Since I can't cancel anything out, I know that I'm going to have an infinite discontinuity rather than a removable discontinuity. An infinite wherever this 7x minus 1 business has a value of 0. So that's going to be at, let's see, 1 over 7. For this problem, I want to know if this function is continuous at both x equals 1 and x equals 3. Well, let's test 1 first. Now, 1 is a border value between the first two rules of this piecewise function. So we have to check the left and the right limits on this and compare it to the function value. Left side limit, as x approaches 1, is using this first rule, this before 1 rule. So that's 3 times 1 plus 2, which is 5. The right side limit at 1 is using this second rule, the after 1 rule, which just automatically gives us 5. These match up, so our limit exists, and it's 5. How about f of 1? Well, that's just using this first rule again, which again would give us 5. So since the limit as x approaches 1 and f of 1 both exist and equal each other, that allows us to conclude that our f function is continuous at x equals 1. Okay, moving on to x equals 3. Left side limit at 3. Now we're using this before 3 rule, which is the 5 again. Next, for the right side limit of 3, we have to use this greater than 3 rule. So 3 times 3 squared, that's going to be 27, minus 1 is 26. Well, that's a little bit different. So since our limit does not exist, because these limits did not match up, since the two-sided limit does not exist, that means that f is not continuous at x equals 3. For this problem, we want to know if this function is continuous at x equals 0. So there's a few ways to do this problem. One way would be to set this up as a piecewise function. So you'd have a rule with negative x over x and another rule with x over x. You could then find the limits of that, and you would discover that the limits were different as you came from the left and the right. But a much simpler way to do this, since continuity also requires the function to exist, is just plug in 0 and see what happens. If you plug 0 in for x, you're going to see that this comes out some kind of undefined, 0 over 0, but that still is undefined because your best case scenario there is that you have a hole, but that would still be some kind of discontinuity. So because f of 0 does not exist, that means our function is not continuous at x equals 0, and that's all we really need to show. On this problem, we're given the graph of big F of x here, and they're told that it's discontinuous at x equals 4. We want to know the reason. So let's go ahead and analyze what's going on at x equals 4. So we see that the left side limit of our function is, let's see, we're approaching 1 from the left, and the right side limit, we're approaching 1 from the right, and we'll also take a look at the function value. So that's going to be f of 1, big F, or big F of 4 rather. That's going to be the solid dot down here, and that's negative 3. Okay, looking at our different answer choices, f of 4 is undefined. Well, that's false. It actually equals negative 3. Option 2, limit as x approaches 4 if the function does not exist, also false. The left and the right side limit both equal 1. So in general, we can say f of 4 and limit at 4 of f both exist. So that means that options 1 and 2 are no good. But having said that, although these both exist, the limit as x approaches 4 is 1. F of 4 is negative 3, so they don't actually equal each other, which means that option 3 is what we want here, them not equaling each other. So that's going to be, let's see, option 3 only, choice D. So we're not continuous at x equals 4 because of choice D. For this problem, we're trying to find a and b values that make this function continuous. In order for this to be continuous, that means that the left-right limits at the border value and also the function value at 5 all have to equal the same number. So let's calculate what all of those are with the a and the b in there and then just set them equal to each other. For the left side limit, we're using this rule where x is less than 5. So that's going to be 5 squared plus 5a plus 1, or 25 plus 5a plus 1, or 26. And then the function value, f of 5, is 8. So we know that this expression and 8 have to equal each other. Let's set them equal. We'll worry about the right side limit in a minute, but let's take care of this first. At minimum, a has to make this whole thing come out to 8. So if we subtract 26, that's going to be negative 18, and then divide by 5, so negative 18 over 5. All right, now we also know that this stuff all has to equal out to the right side limit. So let's take our right side limit now when we plug 5 into this rule here. That's going to be 5b plus 3. And we know that that also has to have a value of 8. It also has to equal the function value. And if it equals the function value, by extension, it will also equal this left side limit that we just found. So plugging that in, we've got 5b plus 3 equals 8. Subtract the 3, that's going to be 5. Divide by 5, we've got b equals 1. So there we have it. B value of 1, a value of negative 18/5 makes this continuous. For this problem, we're trying to figure out an a value that's going to make this function continuous. Since it's a piecewise function, we're going to essentially check out the border value and find the left and the right limit there and also the function value, and just make sure all those things equal each other. So for our border value, we have a, which is ironically the number we're actually trying to figure out. But let's see if we can find the left and the right side limit when x equals a. How do we find those limits? Well, this is kind of a weird setup with rules. We basically have this is the function we're using unless x equals a. In that one instance, we have this little solid dot that goes somewhere else. So if I'm looking to find the limit as we approach a, I basically have to use this function coming from both sides. So my two-sided limit then is just going to be whatever I get when I plug a into this. But if I plug in a directly, then you notice we're just going to get 0 over 0. So before I even plug a into this, let me factor and cancel. That'll be x plus a and x minus a in the numerator. X minus a's cancel. Now we can plug a into this reduced version. That's going to be a plus a, which gives us a two-sided limit of just 2a. All right, so this has to match the function value when we plug a into the function. If x equals a, then we use this rule down here, 8. So that means that 2a and 8 must equal each other, which means that a must equal 4. And if I let a be 4, that's going to make this continuous. Now, in case you're worried about this hole here, you don't have to worry about it because we're actually only going to use this rule specifically when x does not equal this number here.